Why giant whales fear the ocean's smallest creatures reveals how parasites, toxic microscopic algae, and invisible germs can trouble, weaken, and sometimes kill the largest animals on Earth. What a whale does when danger arrives, and whether an ocean giant can survive an enemy too small to see. Picture a blue whale moving through the open ocean, with a body longer than a city bus, a heart roughly the size of a small vehicle, and enough power in its tail to push an enormous mass through thousands of kilometers of water. At first glance, such an animal seems almost untouchable. A shark is smaller, most boats are lighter, and even rough waves appear to roll harmlessly across the whale's back. If danger had to match its victim in size, almost nothing in nature would be able to challenge this giant. Yet nature does not measure power only in meters or tons. Sometimes the most successful attacker is not the one that can bite deepest, but the one that can hide, multiply, travel unnoticed, or turn an animal's own food into a trap. A creature may be no larger than a fingernail, a grain of sand, or a single cell, and still reach places that teeth and claws cannot. It can settle in a fold of skin, enter through a wound, ride inside a fish, or release a chemical that moves silently through the food web. Before we go farther, however, we need to correct one tempting misunderstanding. Giant whales are not frightened of every small animal in the sea. Baleen whales deliberately swim into clouds of krill and copepods because these tiny crustaceans are food. A blue whale can engulf an immense mouthful of water, close its jaws, and force that water out through sheets of baleen, leaving thousands of small animals trapped inside. To the whale, a healthy patch of krill is not a monster. It is dinner. The real story begins when smallness is combined with the right weapon. Some tiny creatures cling to the outside of a whale. Others live inside it. Some do not need to enter the whale at all, because the poison they produce is carried upward through the animals the whale eats. These threats are very different, and a whale does not react to each one in the same way. One of the strangest visible passengers is commonly called a whale louse, although it is not a true louse, like the insects that live on land mammals. Whale lice are small crustaceans called cyamids, related more closely to animals such as amphipods than to insects. Their flattened bodies and hooked limbs help them hold on while their enormous host dives, rolls, accelerates, and crosses stormy seas. They gather in protected places where the flow of water is weaker, including cracks, calloused patches, wounds, the edges of the mouth, and folds near the flippers or other openings. On the smooth skin of a fast-moving whale, anything without a powerful grip would quickly be swept away. So the body of a whale louse works almost like a living climbing tool. It does not need to chase the whale because the whale carries it everywhere. Depending on the species and situation, cyamids may feed on flakes of skin, damaged tissue, or material around a wound. A few passengers may cause little trouble, while a heavy concentration can irritate injured areas and make an unhealthy whale look even more alarming. Gray whales are especially famous for carrying communities of whale lice and barnacles. Researchers have found that particular cyamid species often prefer particular parts of the body, as though the whale were an enormous island divided into neighborhoods. Because whale lice usually transfer during close contact, a mother and calf can pass them between one another while nursing or swimming side by side. They cannot simply leap across kilometers of open water in search of a host, so touch becomes their bridge. Does a whale panic when it meets these little hitchhikers? Probably not in the way a person might panic after seeing an insect crawl across an arm. In many cases, the passengers remain on the whale for long periods, and scientists cannot ask the whale exactly what it feels. Researchers therefore watch behavior, examine skin, study hormones and tissues, and compare healthy animals with sick ones. Gray whales sometimes rub their bodies against rocks or the seafloor, and they may move through water that reduces some external passengers. but scientists must be careful when interpreting such actions. Rubbing could help remove irritating organisms, yet it can also have other purposes. That uncertainty teaches us something important about the word fear. Humans describe fear with language, facial expressions, and personal memories. Whales cannot explain their emotions to us, but they possess brains, nervous systems, stress hormones, strong social relationships, and the ability to learn from danger. When whales face an immediate threat, they can change direction, group together, protect a calf, become quiet, speed away, slap the water, or alter a dive. Those are real defensive responses, although scientists should not claim that the inner experience is identical to human fear. For this reason, when we say that a whale fears a tiny creature, we sometimes mean something broader. Its body detects harm and responds. Its behavior helps it avoid a dangerous place, or evolution has equipped it to resist an attacker. A whale does not need to look at a microscopic cell and think, "I am afraid of that." Its immune system can recognize the invasion, its nervous system can respond to pain, and its learned experience may lead it away from water associated with sickness. Barnacles provide another useful clue. They begin life as tiny, drifting larvae. Then, some species attach to a whale and build hard shells. Adult whale barnacles can become much larger than whale lice, and colonies add roughness and drag to the skin. Nevertheless, they are usually described as epibionts, organisms living on another animal rather than deadly hunters. Their presence can tell scientists about a whale's travels and life history, but they are not normally capable of bringing down a healthy giant by themselves. The difference between an irritating passenger and a serious threat often depends on the whale's condition. Thick skin and a powerful immune system provide protection, but no defense is perfect. A wound caused by a collision, fishing gear, a predator, or disease can create an opening. An organism that was once merely riding on the surface may take advantage of damaged tissue. The problem is not always a dramatic attack. It can be the slow accumulation of stress when several difficulties arrive together. Imagine a whale that has completed a long migration while eating very little, as some species do between feeding and breeding grounds. Its stored energy is lower, and a calf may depend on its milk. Now add a skin injury, many external parasites, unusually warm water, and less food than expected. No single small creature needs to overpower the whale. Instead, each challenge takes a little energy, slows healing, or makes infection more likely. Nature often works through combinations rather than one clear villain. The ocean also contains parasites that spend part of their lives inside whales. These can include worms living in the digestive system, lungs, tissues, or other organs. Some have complicated life cycles that pass through several hosts before reaching a whale. A tiny larval stage may enter a small crustacean. A fish or squid eats that crustacean. Then a toothed whale eats the fish or squid. The parasite has used the food web like a staircase, climbing from one body to the next without ever swimming after a whale. Many wild animals carry parasites without immediately becoming sick, and whales are no exception. A stable relationship can exist when the parasite takes resources but does not cause enough damage to kill its host. Killing the host too quickly would often be a poor strategy because the parasite would lose its home. Trouble begins when the number of parasites becomes unusually high, when they damage a sensitive organ, or when the whale is already weak for another reason. This is how something small can threaten something immense. It attacks a vulnerable system rather than the entire body at once. A tiny worm does not have to pull a whale backward through the water. It only has to interfere with breathing, digestion, blood flow, or the function of an organ. A microscopic pathogen does not need to match the whale's weight. It can enter a cell, use that cell to reproduce, and force the whale's immune system into a costly battle. Whales have defenses against such invaders. Skin forms the first wall. Mucus and normal microbes can make some surfaces difficult to colonize, and immune cells patrol the body. Inflammation helps isolate damage, while antibodies and other immune tools recognize particular threats. Fever and changes in behavior may help some mammals fight infection, although observing these processes in a free-swimming whale is extremely difficult. A veterinarian can examine a dog closely every day. A whale may surface for seconds and then disappear beneath dark water. Scientists therefore behave like detectives working with scattered evidence. They photograph skin conditions, collect a puff of exhaled breath above the blowhole, examine feces, take small tissue samples, measure hormones, listen to breathing, and study stranded animals. Drones can reveal changes in body shape, showing whether a whale is losing weight. None of these clues is perfect alone, but together they can reveal whether an animal is coping with a minor burden or moving toward serious illness. The breath sample is especially fascinating because a whale's blow can carry droplets, cells, and microorganisms from the respiratory system. Researchers can fly a carefully controlled drone through the mist and collect material without capturing the animal. From that brief cloud, they may learn about microbes or health markers inside a creature that is otherwise almost impossible to examine. The giant remains below, while its smallest biological clues float in the air. Viruses, bacteria, and fungi are among the smallest possible opponents in this story. Strictly speaking, scientists debate whether viruses count as living creatures because they cannot reproduce without a host cell. Yet their effect can be enormous. Certain infections can contribute to skin lesions, pneumonia, damage to the nervous system, reproductive failure, or mass strandings among cetaceans. Not every microbe is harmful, and whales, like humans, carry communities of harmless or useful microorganisms. The danger comes from particular species, harmful strains, or an imbalance that appears when normal defenses weaken. Some diseases spread through direct contact, respiratory droplets, contaminated water, prey, or contact with bodily fluids. Social behavior can create both risk and protection. Whales may travel in groups, touch one another, share feeding areas, and care for calves, which can give pathogens opportunities to move. At the same time, social companions can help defend young animals, guide them toward food, and support behaviors that improve survival. The very closeness that makes whale society powerful can also provide a route for something microscopic. What happens when a whale becomes ill is rarely as simple as one dramatic scene. The first signs may be almost invisible: slower movement, unusual breathing, reduced feeding, a change in dive pattern, separation from companions, or difficulty maintaining body condition. A sick whale may spend more time near the surface because deep dives demand energy and careful control of oxygen. It may drift toward shore, where waves and tides create another danger. If it strands, the weight normally supported by water can compress tissues and make breathing even harder. However, seeing a parasite or lesion on a stranded whale does not prove that it caused the stranding. The parasite might be a result of poor health rather than the original cause, or it might be only one part of a larger chain. Scientists examine organs, test for toxins and infectious agents, study injuries, review recent environmental conditions, and sometimes still cannot identify a single answer. The ocean hides evidence quickly, and decomposition can erase important clues. We have now met creatures that climb onto whales and invaders that enter their bodies, but the most surprising threat may not behave like a parasite at all. It begins with organisms so small that millions can exist in a relatively small volume of seawater: microscopic algae. Most phytoplankton are not enemies. They form the base of marine food webs, produce a great share of the oxygen associated with life on Earth, and support the krill and fish that whales need. Without these tiny drifting cells, many giants could not exist. Under certain conditions, however, Some kinds of algae multiply rapidly and form harmful blooms. A bloom does not always turn the water a dramatic color, and not every bloom is toxic. The dangerous species can produce powerful chemicals, including domoic acid or saxitoxin. The algae may be microscopic, but the molecules they release or contain can affect nerves and other vital systems. Here, the food web changes from a staircase into a delivery system. Shellfish, plankton-eating animals, krill, or small fish consume the algae and accumulate the toxin. A larger animal then eats many contaminated prey. The toxin becomes concentrated enough to cause harm, even though the whale never intentionally approached anything that looked dangerous. Its feeding strategy, perfected over millions of years, can carry the invisible threat straight into its body. Explains why fear is not quite the perfect word, even though the title captures a genuine truth. A whale may show clear avoidance when chased by a predator, but a microscopic alga does not announce itself as an attacker. The whale's response may begin only after exposure, through illness, stress, and altered behavior. The fear belongs partly to us as observers, because we understand that an apparently peaceful feeding ground may hide a threat the whale cannot easily detect. There is another layer to the mystery. Changing ocean conditions can rearrange where and when small organisms appear. Water temperature, nutrients, currents, melting ice, and upwelling influence plankton communities. Some harmful blooms are expanding into regions where they were once less common, and toxins have been found in marine food webs far into northern waters. A migrating whale follows routes shaped by memory and the seasonal arrival of food, but the conditions at the destination may no longer match the past. For a whale, migration is already an extraordinary calculation. It must spend energy to travel, time its arrival with feeding opportunities, avoid ships and fishing gear, care for young, and find mates. Add a shifting microscopic hazard, and the old map becomes less reliable. The whale cannot read a satellite image or a toxin forecast. It must make decisions from smell, sound, temperature, prey behavior, memory, and the actions of other whales. Researchers can use tools the whale does not have. They sample seawater, identify algal species, measure toxin levels in plankton and prey, study tissue from stranded animals, and track blooms from ships, buoys, aircraft, and satellites. When these observations are combined with whale sightings and movement data, patterns may emerge. A whale's route, an unusual bloom, contaminated prey, and signs of illness can form a chain of evidence, although each link must be tested carefully. So far, the tiny threats have seemed to hold every advantage. They are numerous, hidden, and carried by currents or food. Yet whales are not helpless. Their bodies are the result of millions of years of exposure to parasites, microbes, and changing seas. Immune defenses can eliminate many infections. Skin heals. Some toxins can be processed and removed if the dose is not too high. Behaviors such as rubbing, changing location, resting, or altering feeding may reduce certain burdens. Most encounters with tiny organisms do not end in death. A healthy whale also possesses something that is easy to overlook: an enormous reserve of strength. Blubber stores energy, a large body loses heat relatively slowly, and powerful lungs and muscles support long journeys. These advantages can buy time for recovery. A mother can guide a calf, and social companions may help an animal remain oriented. Survival is not guaranteed, but neither is defeat. The outcome changes sharply when several pressures overlap. Hunger can weaken immune defense. A wound can invite infection. Noise can disrupt communication or feeding. Entanglement can drain energy for weeks or months. A ship strike can cause internal injuries. Then a parasite, bacterium, or toxin that might have been manageable becomes the final burden. The smallest creature may appear to win, although human-created stress helped prepare the battlefield. This is why scientists resist stories with only one villain. If a dead whale carries many parasites, the conclusion is not automatically that the parasites killed it. If toxin is detected, researchers must consider the amount, the tissues involved, and other injuries or diseases. If a whale is thin, they ask whether prey was scarce, migration was unusually costly, or illness reduced feeding. A correct answer may involve an entire network of causes. Still, there are moments when a tiny organism or its toxin can be deadly. A severe infection can overwhelm the immune system. Heavy parasite loads can damage important tissues. A neurotoxin can disrupt the brain and muscles. A weakened calf has fewer reserves than a healthy adult, while an older or injured animal may recover slowly. Size protects against many physical attacks, but it does not create immunity to chemistry or disease. We can now answer the first great question. Which tiny creatures can frighten or threaten giant whales? Whale lice and other external passengers can irritate skin and exploit wounds. Internal worms can steal nutrients or damage organs. Harmful bacteria, viruses, and fungi can cause disease. Microscopic algae can produce toxins that move through krill, fish, and shellfish. Yet ordinary krill and most plankton belong on the other side of the story, because they nourish whales and support the entire ocean community. The second question asks how something small can challenge a giant, and the answer is precision combined with numbers. Tiny attackers do not wrestle the whole whale. They target cells, nerves, wounds, lungs, intestines, or the immune system. They reproduce, accumulate, or recruit the food web to carry their chemical weapons. One organism may be insignificant, but thousands, millions, or a concentrated toxin can change the outcome. The third question asks whether whales truly feel fear as humans do. We cannot enter a whale's mind, and responsible science avoids pretending that we can. Evidence shows that whales detect danger, learn, remember, experience physiological stress, protect their young, and change behavior when threatened. It is reasonable to speak about fear in an everyday sense, but the most accurate description is that whales have emotional and biological responses to danger whose private feeling remains unknown to us. The fourth question asks what happens during an encounter. With external parasites, a whale may tolerate them, rub against surfaces, or carry marks and irritated skin. With internal infection, the signs can include weakness, altered breathing, poor body condition, or unusual movement. With algal toxins, the danger may arrive unnoticed through prey and later interfere with the nervous system. Sometimes the whale recovers. Sometimes the exposure leaves lasting damage. And sometimes scientists discover the story only after the animal strands. Only one question remains unanswered. Can the smallest creatures actually kill the ocean's giants? And if so, does our imagined whale survive? To answer it, return to the feeding ground where our story began. A great whale enters a dense patch of prey, opens its mouth, and takes in an astonishing volume of water. Among countless nourishing animals are a few that contain an invisible toxin. The whale cannot see the difference, and the first mouthful gives no warning. It feeds again, because leaving would mean giving up the energy needed for migration. More contaminated prey enter its body. But dose matters, health matters, and time matters. If the concentration is limited and the whale is strong, its body may process the exposure, and the animal may move on as currents scatter the prey. If the concentration is high, or if wounds, hunger, parasites, and infection have already taken their share, the same event can push the animal beyond recovery. That is the peak of the mystery. The battle is not decided by the size of the whale or the size of the creature. It is decided by where the attack occurs, how much exposure takes place, how quickly the whale responds, and what other burdens it already carries. The giant wins many of these hidden battles without any human ever knowing they happened. We notice the tragic cases precisely because successful recovery usually leaves no body on a beach and no mystery for scientists to investigate. So did the giant whale survive? In the encounter we have followed, yes. The bloom was scattered before the whale received a fatal dose. Its immune defenses controlled the smaller parasites and microbes it carried, and after a period of slower travel, it continued toward cleaner water. That survival was not a miracle, and it was not guaranteed. It was the result of a strong body, limited exposure, good timing, and defenses shaped by countless generations of whales that faced the same invisible world. Other whales are not always so fortunate. Tiny organisms and their toxins can contribute to severe illness and death, especially when the animal is young, old, injured, hungry, or already fighting several threats. The ocean's largest inhabitants therefore teach us an unexpected rule of nature. Strength is not simply the ability to overpower an enemy, but the ability to detect damage, adapt, recover, and keep moving through a world where danger may be too small to see. The title, Why Giant Whales Fear the Ocean's Smallest Creatures, is not really a story about giants being cowardly. It is a story about scale deceiving us. Krill can feed a blue whale. Whale lice can turn its skin into a habitat. A worm can use its meal as transportation. A microbe can invade its cells. And a single kind of algae can place poison into an entire food chain. The whale is bigger than every one of these organisms, but it is still connected to them by every breath, every mouthful, and every kilometer of water it crosses. Once we understand that connection, a whale no longer looks like a lonely ruler floating above the rest of nature. It looks like a moving ecosystem, carrying passengers, fighting invaders, feeding on vast living clouds, and depending on microscopic producers at the bottom of the food web. Its survival proves that nature's greatest power is not size alone, but balance. And when that balance holds, even an invisible enemy cannot stop the giant from rising again to breathe.